Hello and welcome. Today we get to work with section 4.3 on complex zeros. So we'll take a look at complex polynomial f of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus down to plus a sub 1 x to the first is just typically written as x plus a naught x to the 0 is a 1 and times 1 we typically wouldn't write. You may say, okay, that looks familiar. That looks like the polynomials that we worked with in chapter 4 already in section 4.2. It is close. However, here a sub I is a complex constant. So in other words, we're allowed to have constants of the form a plus bi instead of just in the set of reals. As usual, a sub n we're assuming is non-zero, otherwise we've knocked it down to an n minus 1 degree polynomial, and of course n is in the set of natural numbers. We're not allowing anything raised to, say, a negative power or a proper fraction, a natural number only. So R is a complex zero if f of R is equal to 0. So the fundamental theorem of algebra with factor theorem. All complex polynomials f degree n at least 1. We're talking degrees, so n, of course, is in the set of naturals. Can be factored into n linear factors. We are not guaranteed that they are unique. So in other words, any complex polynomial we can break down into a sub n, x minus r sub 1, x minus r sub 2, times times x minus r sub n. So we can always break it down into linear factors. They may just end up kicking us into the complex numbers for these constants. Now, one handy tool that we have here is also the conjugate pairs theorem. If R is a plus bi is a complex zero of f, then R conjugate, which recall is a minus bi, is also a complex zero of f. So if 6 minus 2i is a 0, 6 plus 2i must also be a 0. If negative 3i is a 0, positive 3i is also a 0. And there's a nice little corollary to that. All odd polynomials have at least one real 0. So they can't all be imaginary zeros because of the conjugate pairs theorem. If we have something that is a complex number that is a 0, its conjugate is another 0, so they always come in pairs. In other words, multiples of 2 for those. So if we have an odd degree, at least one won't have a partner. So for example, if we're told that a polynomial of degree 7 has zeros, x equals 7, x equals 2 minus I, x equals 3i, and x equals 5 plus I, they could ask us to find the remaining zeros. Well, 7 is just in our regular, nice, neat, pretty, compact real number system. The others are outside of the reals but still in the complex, so their conjugates are also 0. So x equals 2 plus I also has to be a 0. If x equals 3i is a 0, then x equals negative 3i is a 0. If x equals 5 plus I is a 0, x equals 5 minus I must also be a 0. So there we have our 1, 2, 3, 4, 5, 6, 7 zeros of the 7th degree polynomial. They could ask us to find polynomials with certain properties. So for this next one, we'll be asked to find a 4th degree polynomial and zeros. X equals 5, x equals negative 5, x equals 2 minus I. So notice they only gave us 3 of the zeros. So we do know by the conjugate pairs theorem that our missing 0 was x equals 2 plus I to be another 0. So then making our polynomial in this section is the same as it was before. We are now just allowing ourselves to have complex numbers as our constants. So if x equals 5 is a 0, x minus 5 is a factor. If x equals negative 5 is a 0, x plus 5 was a factor. If x equals 2 minus I is a 0, then x minus 2 plus I is a factor. So think of setting each of these guys to 0. A is our just leading coefficient. And for our last one that we had to figure out, then x minus 2 minus I had to be our other remaining factor. And then we can just multiply it out. So I'll just hang on to the A. And a little hint here, these are a little bit easier if you kind of group them together with conjugate pairs. So the x minus 5 by the x plus 5 is x squared minus 25, since the outer and inner cancel. And then we'll just go ahead and distribute this. So we have x squared minus 2x minus ix. So we brought the x to all three. Now we'll bring the negative 2 to all three. So negative 2x plus 4, and finally plus 2i. And distributing the I plus ix minus 2i and minus I squared is really a plus 1. Close up the parenthesis. So f of x is now a by x squared minus 25 by, we get lots of nice, neat, pretty cancellation. So the x squared, only one of its kind, I'll just kind of check them off as I go. We have minus 2x minus another 2x, so minus 4x. Then we have minus ix and plus ix, those drop. We have plus 2i and minus 2i, those guys drop. And finally, a plus 4 and a plus 1 will give us a plus 5 there. So then f of x is, I'll hold on to the a and just distribute the x squared, then distribute the minus 25. So x to the fourth minus 4x cubed plus 5x squared. So distributing the x squared, and now we'll distribute the minus 25. So minus 25x squared plus 100x and minus 125, and just hit our like term. So f of x is whatever non-zero value we pick out for a, by then x to the fourth minus a 4x cubed minus 20x squared plus 100x minus 125. So that's a polynomial fourth degree. It has all four of the leading zeros, the three they gave us, and the fourth one that we found using the conjugate pairs theorem. Now our rational zero theorem from before still does exist. It still does help us find zeros, both real and complex. So if they ask us to find all the zeros, they then mean both real and complex. They will typically just say find all the zeros or find all the complex zeros. So let's see, we'll have f of x is 3x to the fourth plus 5x cubed plus 46x squared plus 80x minus 32. So our possible rational zeros, so p, all the factors of 32, plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32, and q plus or minus 1 or 3. So p over q, each of these over 1, and then each of these over 3. So plus or minus 1 over 1 is 1, plus or minus 1/3. Plus or minus 2, plus or minus 2/3, plus or minus 4, plus or minus 4/3, etc. So there's our list of p over q's. On this one, we start plugging and chugging, and eventually we hit on f of -2 being worth 0. So that's just plugging into the calculator, you'll find that value. So we have a -2 outside. Fourth power coefficient is a 3, third power coefficient a 5, second power coefficient 46, first power coefficient 80, and our constant -32. Fill in zeros if we have any missing terms. So bring the first one down, then multiply and add all the way through. So you have a -6, -1, +2, +48, -96, -16, +32, and there's that big fat 0 we should expect to see at the end. You know you did your synthetic division correctly if you get the same 0 you got out of the calculator for your remainder. So now we can say that we know that f of x is x plus 2 by 3x to the, so here's our remainder, constant, first power, second power, third power. 3x cubed minus x squared plus 48x minus 16. And then this one is actually just factorable by grouping. So hang on to your x plus 2. From the 3x cubed and the minus x squared, grab an x squared, leaving us a 3x minus 1. From the plus 48x and minus 16, we can factor a 16, also leaving us a 3x minus 1. So f of x then is x plus 2 by 3x minus 1 by x squared plus 16. So finding all of our zeros, x plus 2 equals 0 because this is a 0 of x equals negative 2, 3x minus 1 equals 0, so x equals 1/3, x squared plus 16 equals 0, x squared is negative 16, square to both sides, plus or minus on the side with the constant x equals plus or minus 4i, so there's our 4 zeros. Now they could also have asked us to factor that. So they could say find all the zeros. If they say find all the zeros, we found all four of them there. If they say instead to also factor this, we have one more step in there. Then f of x, if asked to factor, would be the x plus 2 by the 3x minus 1 by the factored version of this, which would be if x equals 4i is a 0, x minus 4i was a factor. If x equals negative 4i is a 0, x plus 4i was a factor. Okay, so in 4.3, I would recommend 1 through 6 all, 7 to 39 odd, and I'll try to create a similar one on the MyMathLab for the MyMathLab fans. If you have any questions, please get in touch. I almost forgot the last chunk of the assignment there. The last chunk would be 44 to 48 as well. 44 through 48. If you have any questions, get in touch with me. Otherwise, I'll see you next time.